always a little bit strange because we've been talking for 20 minutes now about the final project and I haven't recorded it, but for those of you who missed today's lecture and want to hear about the final project, you can either email me or post on the forums. But today's going to be a nice lecture. So today is sort of the first lecture that we're sort of going to get deep into this Wainwright and Jordan text. And hopefully everyone has read the first 3 chapters in this book, or at least started them. And so here we are on the second column of the class. This means officially we've started the second half of the class now. Isn't that great? You might think we're going to run out of room from this slide, but interestingly enough, the font has this magical capability of shrinking to fit any available amount of text that lives on the page. So we will not run out of room, although the font might shrink, and you might need glasses by the time we get to the end of the class. So just to review, so remember we had we started talking about approximate inference. We're in this realm outside of the yellow region that we saw in this picture of the time-space trade-off picture, where we can no longer do exact inference. And we saw that there are 2 different approaches to doing approximate inference. The one approach is to do an exact solution to an approximate problem, and where, for example, you do structure learning or you come up with some other model which is, for one reason or another, tractable to do exact inference, and then you do inference on that. And that is one approach. The approach that we're going to be taking for the most part in this class is to do an approximate solution to an exact problem. So we're going to take the original problem and come up with mathematical ways of say, approximating it. And the first half of the second half of this class is going to be on this Wainwright and Jordan text, which involves things like variational approaches and linear programming relaxations of the problem and loopy belief propagation and various properties associated with the log partition function. And then the second half, or part of the course, is going to be actually more on, actually I take this back, the second part is going to be more on this bit here. It's going to be more on functional restrictions to the model. But again, it's no longer the case that we're in this region where we're exact. So remember, so the fundamental message we defined, we're going to talk about belief propagation, loopy belief propagation. There's a message, and it's defined on an edge, which basically consists of pairs of nodes. And if it's a tree, then we can get the marginals. And we saw last time also that if we have higher order potentials, we can reduce it to a pairwise graph. And we talked a little bit about the semantics of a Markov random field. There are these different strategies where we can deal with higher order ones. The one that we're going to do is this one up here. It's number 1. So we're going to transform, and we're going to assume that we're dealing with pairwise potentials. We also talked about this idea of a state representation, where essentially you have a big set of all of these messages, which is this thing here. And that can be seen as a state vector. And every time we send a new message, we update the state vector, going from mu sub t to mu sub t plus 1. And we could also potentially think about sending messages in parallel, where multiple messages are sent. And maybe there's some way, we thought, of composing the message sends. And if it's the case that we can express message sends as a matrix multiply, as a big matrix multiply, then composition means matrix matrix multiply. And it should be possible to send multiple messages and thereby move us forward in the state evolution. And the nice thing about that is that it sort of allows us to sort of talk about sort of linear dynamical systems as a strategy for dealing with and understanding when do message passing strategies converge in some way or another. And we saw that indeed, yes, it is possible to show that a message can be seen as a matrix vector multiply, where we take all of these messages here and lump them into one vector, and then this new message is basically this matrix vector multiply here. And we can also group multiple messages together. So that you could think of this little guy as being one little sub-matrix within some large matrix. And if we do a bunch of messages, each message would be represented as a large matrix with a little sub-matrix being active and everything else being the identity. And we multiply all these large matrices together, and we get essentially then a single matrix multiply over on this large state vector, which then does all of these messages in parallel. Okay. Okay, and ask questions if there's anything. So then we saw that if it's a tree, that if we run this some number of times, namely, if we run all messages in parallel and we do the matrix multiply d times, where d is the diameter of the tree, then essentially we'll have converged, meaning that any additional messages thereafter sent, or in other words, any matrix multiply done thereafter, where a matrix multiply corresponds to a message or a collection of messages thereon, would not change the state vector, which then sounds to us like an eigenvector eigenvalue problem. Okay, because that we can now use the tools of matrix algebra to understand convergence. But the problem happens, and the difficulty happens, when we start having graphs with a cycle. Like, first of all, if there's a cycle, we can't even begin to send messages because we don't have any messages received. When it's a cycle, even like the simple, humble little for cycle, we actually get to a deadlock situation where no message can go because we've never received a message from anybody else. But what we can do to break the deadlock is to just sort of arbitrarily initialize the messages, just to say, let's say that all the messages are 1, and then we could start sending messages. So then the question is, what happens after d steps? Okay, but then really, well, what is d? What is the diameter of a cycle? How many steps? So we need to sort of understand what happens there. And the point is that what could happen after d steps, or after any number of steps, is that it could oscillate. It might never ever converge. And here's an example. Let's consider any odd length cycle. So C3 would be a cycle of length 3. C5 would be a cycle of length 5. And it suffices for us to do an odd length cycle. So an odd length cycle would be something like I, J, and K. Right? And then you go back to I. So there's an odd length cycle. It's length 3. And let's just assume that, let's initialize the messages to be this 1, 0 vector. So every message is initialized to be the vector. And all variables are binary, so all messages are vectors of length 2. Okay? So we initialize the messages to be that. And let's assume also that we've got this pairwise edge function. So we've got potential functions that are of this form. This form meaning right here. So it's a little 2 by 2 matrix, and it basically says how to go from one message to the next message. Okay. So here's the actual expression, the mathematical expression for a message send, which when we see as matrix multiply, again, just corresponds to this. So we go from ij, we start with message ij, we hit it with this matrix, and we get the message for jk. And then that's the new message, and then we just keep going around the cycle. And we keep hitting it with this matrix multiply again, where the matrix corresponds to this thing here. Okay? Any questions? So a little bit more notation. So mu t of I sub j is the message at the tth iteration. So what we mean by the tth iteration is like we send a message, and then we go all around, and we come back. That's the t plus first iteration. And then we go all around again, and then we get the t plus second iteration. Okay, so every time we just keep going around the cycle. Every time we come back to the same message, say in this case ij, we increment t, and we start with mu naught being this starting state, which we mentioned before, which is 1, 0. So what we end up getting, yes, question?
So we're not sending all possible messages at the same time in this case.
In this case,
that initial point, and then you start in a sequence.
Well, let me ask this question after we do the end of the slide, and tell me if you think it makes a difference. Okay. But let's for the moment, you're right. Let's just go around here. But then to get back to your question, it's a good question. Would that help? Okay, or would that change things? So what we're going to see in this case is that at time 1, the message is going to be at configuration 0, 1. And at time 2, the message is going to be at configuration 1, 0. And at time 3, the message is going to be at configuration 0, 1. And you can see then we're back to where we started from. And what's going to happen is that the messages are going to oscillate forever, and we're never going to reach convergence. I mean, here's the cycle, ijk. And you can see that just starting with the t plus first guide ijk. So that's equal to this composition of these three matrices, right? So it's that's equal to I'm going to need to start getting glasses because I can no longer read my own iPad. This is the first matrix multiplied times the message from k to I. And then message from k to I is this bit, which then gets multiplied by another matrix multiply. And then that bit corresponds to this whole thing, which gets multiplied by another matrix here. And then when you just cube the matrix, they're all the same matrix, right? So you just cube this. So 0, 1, 1, 0 cubed, or multiplied 3 times together, essentially gets you the same thing. And so essentially we're back to just looking at this is equal to this matrix times this, which basically, as you can see, just flips the 1 and the 0. And we just oscillate. And therefore never converge. Now, how this basically seems like a problem, right? Because it's saying we know that if it's a tree, that if we send D messages in parallel, then we'll converge. Or if we do the MPP strategy, we will converge. Whereas we have a simple cycle, and we already found a spot where we don't converge. Now, this was a problem in the 1990s. This is a little bit of a historical perspective. So in the communications literature, in the communications field, there were people were trying to develop better communication systems from, say, point A to point B. And in around 1995, I think 1994, 95, people started finding that there were two classes of codes. One was called a low-density parity check code, LDPC code, and another was called a turbo code. That these codes were able to sort of, if you send messages, if you sent a message, this is not this kind of message, but if you sent a piece of information over a noisy channel and you encoded redundancy bits according to these codes, if you decoded at the receiving end and you used loopy belief propagation, at least what was discovered to be loopy belief propagation in the 90s, it worked really well in the sense that you were able to recover the signal with very, very high fidelity and a relatively low rate. And there was this sudden jump towards the Shannon communications limit on a noisy channel. And this happened in the mid-90s. These days, of course, all of this stuff exists in all of our cell phones and everything. But at the time, it was a major, major improvement in coding theory. And basically, these codes, essentially, what was discovered in the mid-90s is that these are basically big, giant, sparse graphical models. And the decoding algorithm, the thing that actually, essentially, when you take a noisy instance of the signal and you're trying to get back the bits that you actually sent, you're essentially doing loopy belief propagation around this loopy graph. Now, this was something, it was a confluence of events, because the loopy belief propagation algorithm was the same algorithm that was originally suggested by Yuda Perl in 1988 in the context of artificial intelligence and Bayesian networks. And Perl suggested, well, if you have big graphs, he sort of implicitly knew that you get to these very difficult complexity problems if you don't have a tree, or if you sort of triangulate the model, it gets difficult. And Perl just said, just keep sending messages and just loop around for a while. And then back in 1962, I think it was, to 63, an information theorist named Bob Gallagher had also suggested, in the context of coding, communications theory, doing messages of this form, although he didn't use that language. He just said, just keep sending these things around. But at the time, computers were nowhere near powerful enough to actually see whether or not that strategy would work. But by the mid-90s, people thought it would work, or found that it did work. And also, people found that it's actually the same thing as loopy belief propagation. And there was this connection between the artificial intelligence community, the graphical models community, and the communication theory community. So, but no one understood why. So there was this big quest to sort of understand, why is it the case that when you have graphs with loops and you run loopy belief propagation, why is it the case that it just seems to work in practice? And especially when you come up with really easy examples, like the one we just showed here, showing non-convergence. So not only does it converge, not only, like, one thing you might hope for is that it converges, and it converges to the wrong answer, at least, right? But here it doesn't even converge. whether or not it converges to the right or the wrong answer. That's not even a question we can answer because it doesn't converge at all. So one thing that one might want to do is sort of damp the message. And so let's say that gamma is some value between 0 and 1. And basically when you have a new message, say t, you take the old message and you mix the new message with the old message together in this convex combination. That's sort of like a damping. It sort of like smooths things over. And that's actually something that can help, but that's fairly heuristic. And there's sort of a folkloric knowledge which basically says that if it's the case that you converge quickly without damping, the resulting marginals maybe are good. And there have been some empirical studies that have shown this. But this wasn't something that was really, just the simple damping idea wasn't well understood. We were interested in sort of understanding better about when convergence happens and why. And so other sort of strategies that people suggested were maybe, well, why do you do that message schedule? Maybe you could like wiggle back and forth a little bit, or should you go around the loop, or should you do it in parallel? Those generally don't change things. I mean, the thing that you were suggesting before about doing it in parallel, would that change this oscillation problem? With the wrong initialization, every time you do a parallel, you just keep getting, everybody would swap at every step. So the point is that parallelism is not a guaranteed solution to the problem, nor does it lead us to sort of a mathematical understanding of when this does or doesn't occur. Question?
I wonder, just for previous slides, I wonder, does that mean if initially I just send the eigenvector of the matrix, then that means I'm done because it needed it kind of converting?
Yes. So you are anticipating what's going to happen in 2 or 3 slides. So that's exactly right. Obviously, it's sort of related somehow to the eigenvectors. And so what we're going to do is formulate the problem in a way that we can at least state a theorem that relates it to this. Yep, question.
So we can also like do a diagnostic check, right? Like we have this huge message matrix, and if we try to figure out the eigenvalues and see one eigenvalue is greater than 1, that means that Markov chain doesn't have a steady state distribution.
Yep. That's right. That's right. That's right. So I mean, I think by sort of saying, oh, this seems very much like an eigenvector eigenvalue problem, already you guys, which is great, are sort of thinking along those lines. But back in maybe the 90s, I don't know, it's hard to always put yourself, I mean, in hindsight, things seem obvious. But at the time, it's hard to sort of imagine. But first of all, before we even do this, let's just go forward. One simple strategy, one simple way out of this would be to initialize differently. So if we initialize to 0.5, then we've converged, right? And then basically every matrix multiply is going to change the solution. And also dampening, if we do the right damping, then that's also going to end up with this configuration. But the question is there a better way of characterizing this? Okay, and that's what we want to do. And those are the things that you guys are already thinking about and suggesting. So first of all, let's start. Now this is an important thing because let's start with a graph with a single cycle. Okay. Now what does that mean? It might mean maybe I just want to draw this figure here. It might mean that we really do have a single cycle. Or it could also mean that we have, it's not just a single cycle, but off of every node we have, say, a tree hanging off of every node. Or a forest. So you can see that there's a black cycle and a red tree. And this is something we can also deal with right away, because what we could start doing is we could just start sending messages using what we know, using the message passing protocol, sort of collapsing the cycle down to a single node. I don't have to draw all these green arrows, but I think you basically get the idea that essentially all of the messages get sent down to a single node, and what we're left with is the single cycle, which is the black cycle. Okay, so that basically allows us to essentially, as long as we only have one cycle in the graph and everything else is a tree, in other words, if you condition on that cycle, what we're left with is a forest, that's something we can deal with. And so what we're left with is the cycle. And then we're going to consider what happens when, to this message, as time increases. And without loss of generality, let's assume the cycle is of length L, and we're interested in the message from L back to 1. So here's the cycle. The nodes are 1, 2, 3, 4, up to L and to L back to 1. So in some sense, like if this is the cycle around here, this is L, and this is 1, we're interested in this message there. So the dynamics are, we start at the message from L to 1 at time t, we end up with a message from L to 1 at time t plus 1, and we multiply all of these matrices between the two. And so we get one matrix M. So we get, this is really the expression here that we want. The expression we want is, let me just do it in a special color. This is equal to this. Okay? And the question is, will this converge to anything? I mean, in some sense, when you look at it like this way, in this way, you start immediately thinking, oh, eigenvalue, eigenvector problems. Eigenvalue is greater than 1, eigenvalue is less than 1, all this other stuff. And indeed, that's what you get. You get, you can essentially, first of all, acknowledge the power method lemma, which is a standard method in linear algebra, which we're not going to prove, but basically it says the following. It says that if you've got a matrix A, okay, and you have essentially a set of eigenvalues which are distorted in decreasing order, and you have a set of corresponding eigenvectors, and you have a strict relationship between the first and the second eigenvalue, so that the first eigenvalue is strictly greater than the second eigenvalue, at least the magnitude of it. And then you do an update of this form. Now, alpha could be some constant, and in general, what we're going to be doing is alpha is going to be like a normalization constant, right? So like, in order to make sure these things don't blow up, and you can sort of, in some sense, deal with like the eigenvalues being greater than 1 or less than 1, alpha essentially makes it such that that's not a problem. So you can even deal with eigenvalues greater than 1, because when you renormalize, these things are not going to explode, so that it's, you know, these are marginals or something. So alpha is set accordingly, so that you don't blow up, which equivalently can be seen as a restriction on the matrix. So then when you do this update, and you repeatedly do this update, we just keep hitting the dynamic by this matrix, you know, a squared, a cubed, and so on and so forth. What that converges to is a multiple of x1, basically the eigenvector corresponding to the largest eigenvalue, if it's the case that you initialize to be some linear combination of the eigenvectors, and as long as it's the case that that first eigenvector has some representation. So in other words, as long as beta 1 is not 0, so that you have some initial, you're pointing, at least you're spanning that dimension of that first, or that direction of that eigenvector. And moreover, you've got a convergence rate. How quickly does it converge to that? It's a geometric like convergence rate, and it's based on the ratio of the second and the first eigenvalue. Okay. So using this lemma, we immediately get the following theorem, which we're only going to state, we're not going to prove. But it should be pretty clear based a consequence of this. So basically, first of all, it says that this message, the first message, converges to the principal eigenvector of the matrix M. So M is essentially this big matrix of all these messages multiplied together. And this one, the second message, 2 to 1, converges to the principal eigenvector of the transpose of M. The convergence rate is determined by the ratio of the two largest eigenvalues. The diagonal, it turns out, is going to correspond to the correct marginal at x1. This is only at x1. And then the steady state pseudo-marginal. So basically what's going to happen is eventually, if it does converge, we're going to get to this point where we're going to reach a steady state at x1. And the pseudo-marginal is going to be this mixture of the true marginal, p of x1, and this other guy, q of x1, which depends on the rest of the matrix, this guy here. And the mixing ratio is going to depend on how much bigger the largest eigenvalue is from the rest of the eigenvalues. Okay, so what this means is the following. I mean, so the good news is that you've identified conditions for which loopy belief propagation is going to converge on this type of graph. And you've actually characterized what it converges to some extent. You've also characterized possibly how distorted what it converges to is going to be based on beta. And you've also characterized when it's, at least a sufficient condition for it to not oscillate. So that's good news. And in fact, just going back to our oscillating condition, why is it the case that this guy oscillates? Well, if you look at this matrix, the row eigenvector matrix corresponds to this, and then the corresponding eigenvalues are -1 and 1. And so you see that you don't have a strict magnitude inequality between the first and the second eigenvalues. So in other words, we don't have the absolute value of lambda 1 strictly greater than the absolute value of lambda 2. And so therefore, we're not going to have that convergence condition. But it is the case, however, that any uniform vector, like what we tried before, the 0.5, has essentially converged. Right, so anytime you start with a flat distribution, it's going to converge. But we don't have this guaranteed property of convergence from the previous theorem, because, again, we need that condition. Now, so that's all the good news. Now, the bad news, of course, is that there's several bits of bad news. One is that we're not guaranteed we're going to converge to the true marginal. Right? I mean, you could, the reason why you establish these potentials that relate the random variables is maybe because you've learned it based on the data. The data says this is what it should be, or because you've specified it because of your application, or if it's a communications setting, you have designed your graph to do this for a particular function. And so you don't really necessarily, if you're paying attention only to the machine learning problem or to the design of your model, you don't have control over what m is going to be. And so therefore, you might not have these properties being true. And so therefore, you might have an arbitrarily poorly distorted version of the marginals when you're done, if you converge at all. And then the second major problem with this is the following, is that this is only for one loop. What if you have 2 loops? Or 3 loops, or you have a graph with lots of stuff and lots of loops. And most graphical models, you can see, when you're not triangulated, there's going to be lots and lots of cycles, and there could be a huge number of cycles. And so this is an analysis that doesn't help you when you have lots of cycles. And so suddenly you might think, finally, solace with matrix algebra. But in fact, what you've got is complexity, more complexity than you can deal with matrix algebra. So, but at the same time, this was like a very classic result that was highly celebrated, because it was one of the first. Now what we're going to do is we're going to skip ahead, and so we're going to sort of skip ahead maybe about a decade almost, and we're going to start looking at this book by Wainwright and Jordan, which I think sort of at least sort of gives you a really nice sort of compact single source view of for the most part our understanding of the field as it stands still today. There's been some advances since then, but I think that this is still a pretty modern text, and a lot has been done since that first result. Like, for example, we'd like to characterize loopy belief propagation's convergence if it happens for graphs that are more general than just a single loop. And maybe when they are the correct marginals or when they're not the correct marginals, or is there a way we can actually come up with some bound on the marginals and understand this whole problem better. And so in order to do that, we need to develop a little bit of a background on exponential models. And the reason why exponential family models are useful is because they, on the one hand, lead to sort of a unified mathematics of how do you approach this problem, how you approach analyzing this problem, but at the same time, they're very, very flexible in the sense that they can represent most of the problems that we're interested in, including ones where you have zero probabilities. Okay, so any questions on that, what we've talked about so far? Okay. So let's talk a little bit about exponential family models. This is a very, very big topic in statistics, and we're obviously not going to be able to do them justice in one course, let alone one lecture. But let's just talk about it for a bit. So, and this is also going to be our morph from the current notation that we've been using to the notation that they use in the Wainwright-Jordan book. The notation isn't so drastically different, but I will point out the differences as we go along. So, first of all, we start with a collection of functions. So phi now is a vector of functions indexed by this script I. So I is the index set, and it's of dimension d. So we have d such functions. So whenever we see phi, we're looking at a vector of size d. And each such function, each phi sub alpha, is a function of x. And so here's the notation. And this is a very general thing. Like, so alpha essentially determines the function. In general, x is our big vector of random variables. So we still might have, I think the notation they use is that x is of dimension m. I think we were using n. But in any event, the book uses m for the dimensionality of x. And so x could be this very high dimensional vector. And phi is a function of x. But in fact, phi typically will only look at a subset. In other words, so phi sub alpha might only really depend on x sub c sub alpha, where c is some subset of the indices of 1 through m. And in general, a subset here. So again, this basically means that m, we've got some graph, is equal to v of g, and g is the same graph for a graphical model that we've been talking about. Yep.
I'm sorry, I just wanted to ask a question on the 3-cycle thing. I was
Yep.
just thinking about it. So clearly it will keep oscillating because there is no setting of the variables that causes a unique maximum, right? Like there are multiple settings that lead to the same maximum. It's either like 1, 0, 0 or 0, 1, 0 or 0, 0, 1. So maybe it is because the maxima is not like, there is no unique maximum. Is that why it can't?
Well, remember, we're doing summing. I don't know why you were thinking maximum. So what we're trying to find is the marginal, is a marginal. So in other words, what we're trying to get at is, as a configuration, this reparameterization, which we talked about last time, a reparameterization of the potentials so that the potentials could be proportional to the true marginals on those two random variables.
Yeah, the marginals are not even seeming unique. Like it could be that one is 1 by 3, 2 by 3, and the other two can be the opposite,
Well,
and so on.
well, there is a marginal in the sense that if we defined a probability distribution with this set of potentials, right? And then we did do elimination. We would end up courting. We'd end up getting a marginal over 1, 2, and 1 and 2, 3, and 3, 1. We'd get a and that would be something that is a marginal for that three variable random distribution. But the point is that we're not converging to anything. It's oscillating, so we can't have actually reached that marginal. Okay. So there will be, think about it this way. So let me.
Upon the variable you eliminate, you will get different marginals. That's how I can see it. Will that happen there?
No. So let me just do this. Let me get a piece of paper. Piece of paper. So we have P of x1, x2, and x3, which is equal to 1 over z. So z is a normalization constant, and whatever these potentials were, phi of 1, 2 of x1, x2, phi of 2, 3 of x2, x3, and phi of 3, 1, x3, and x1. So that's a valid probability distribution. And if I basically compute p of x1, x2 by summing over x3 of p of x1, x2, x3, that's unique, right? This is it's a perfectly valid probability distribution whose marginals agree with each other, right? Z is this thing which sums over all variables. The point of this loopy belief propagation is that we're not going to ever converge, so clearly we're not going to reach a state where it's even possibly proportional to the marginal, because we're never going to get there. So, but these marginals are going to be unique, okay? That doesn't mean that this always happens. It means that it can happen, right? So it
as a kind of replacement of the marginals, I can do the maxes, right? I can just replace the sums with the maxes anyway. So
yeah, but that's a different problem, right? So we're not doing max marginals. We're doing just the sum marginals. These are the marginals we want. I mean, I don't know why you're thinking in terms of max, because that's not what we're asking for at this moment. We're asking for this marginal, the probability distribution over all pairs. That's the goal of this particular problem. Right? I mean, you might, for example, change the desire to the max marginal, where instead of this summation down here, you do a max over x3, and that would be a max marginal. What happens there, I mean, that of course can change. I mean, if you're changing the semi-ring, you might change the convergence properties potentially. But what we're just showing is an existence case of non-convergence. That's the goal of that exercise, to say that it's possible to never ever converge with loopy-loop propagation. Okay. So, okay, so where are we on this thing? Okay, so we also are defining, this is going to be a little bit definitional. This is always a hard thing to do when you are giving lots and lots of definitions, because there's lots of terminology. But basically, theta is what's going to be called a vector of canonical parameters, and it's going to have length equal to d, the size of I. And theta lives in some subspace, some subset of r to the d, so omega. Okay. And then the exponential family model, let's zoom in on this and highlight it in friendly green. It has the following form. So it's p sub theta, where theta is the canonical parameters. And it's basically taking the e exp of this quantity. Right? And this simple little equation is vastly general and powerful, strangely enough. And so a sub theta, it's a function of the theta, is the thing that makes it normalized. So in other words, it makes it a probability distribution. It's what's called the log partition function. And we will be spending a lot of our time talking about the log partition function. Now, one thing to note here is that in the past, we used phi as a factor outside of the exponent. Now we're using it as a thing inside of the exponent, which is involved in a dot product. The other thing that you might wonder about is this expression here. This is just the inner product. So it's the sum over I, theta sub I, phi sub I of x. Okay. Where I is in script I, or alpha. I guess you could use alpha, whatever. It's just some index variable. So it's the dot product of the parameters times the statistics, or the feature functions. These are sometimes called sufficient statistics, and statistics, or they're called features, or potential functions, depending on if you're in the statistical physics literature, the statistics literature, or the applications literature. Okay, so oh yeah, there's one more guy down here. This is a vector of sufficient statistics. And again, it's important to realize that each phi sub I might use some or all of the vector x. So in other words, it's a function from the domain of potentially all of x to the reals of dimension d. Okay. So now we've got a graph, and we've got a set of cliques in the graph. So the question is, how does it relate to the cliques? So in order to respect the graph, what must be true? I mean, you should be able to answer this question. In order to respect the graph, to factor with respect to the graph, it must be the case that each one of these sufficient statistics never involves variables that span outside of a clique in the graph. So that basically means that if we have any particular index alpha, and we have this feature function, which is a function of x sub c sub alpha, we must have that there exists some clique in the graph such that c sub alpha is less than or equal to c. So like if you have a clique, let's say you have four variables which are connected to a clique, it must be the case that, I mean, you very well could have each one of the c sub alphas correspond to the edges, right? These are all like edge potentials, but they all constitute things that turn into the clique when you union them together. But on the other hand, and this is very typical in this case, you might have different index sets that have more than one feature for a given clique. So in other words, we might have C sub alpha 1 and C sub alpha 2 being exactly the same set. This thing here. Which might seem to be redundant, right? You might say, well, why would you need that? Why not just sort of put them in one thing? You're going to see why, because we might have a distinct parameter associated with it. Because what you do with a random variable or a cluster of random variables might depend very much on the value of the random variables. And oftentimes, like these feature functions, these sufficient statistics might just be indicators, might just be binary functions that indicate that the random variables take on a particular value. And you have a parameter associated with the random variables taking on a particular value. So in such case, this would be very common. In fact, you'll have quite a few of them that satisfy this condition. So let's do an example. I think this is an example. So a simple scalar discrete random variable that has k values. And I think it's probably safe to just say this is R, because we've been using R in this class so far. So there's R possible values in the random variable. And you might have a feature function, alpha sub I. I mean, there's only one random variable in the whole graphical model, right? So you can never have a C sub alpha that has anything other than that random variable in it unless it's a constant. And so you have alpha sub I being an indicator that that random variable is equal to I. So you have two things. One is that you have, first of all, that the number of random variables in C sub alpha is always equal to 1. And also you have that C sub alpha is equal to C sub alpha prime for all of alpha prime in the script set I. But that doesn't mean that they're the same statistic. That doesn't mean they're the same feature. Each one is just an indicator of a random variable being a value. And that means that each value of a random variable can have its own parameter associated with it. Now that makes a lot of sense, because if, let's say you have a multinomial distribution, you want to say, what's the probability of it being this and the probability of it being this, and so on and so forth. And if you have a multinomial random variable with k possible values, then you have there are sort of k minus 1 unique parameters associated with that, which sort of define where you are in the simplex. And here you're saying you have a parameter associated with every possible value. But then when you normalize, you can see that in some sense you're living within this lower dimensional space. And we're going to talk a little bit about that as well in a second. So you could think of these things as being cliques in some graph, but they're not necessarily max cliques. And I think that should be clear. And again, the important thing is that you're not necessarily dealing with triangulated models. You could have 4 cycles with edges, and so you could have features. You only have features corresponding to the edges in this 4 cycle. The key thing, again, is that by this factorization theorem, which we've only sort of implicitly defined, the Hammersley-Clifford theorem, it's basically you have a guarantee that P lives in the family of the graph and the Markov random field according to factorization, where this is the graph, and basically what happens is that this set here forms an edge clique clever, so that if we for every one of the C alphas, if all of the random variables that are in any C alpha are connected together by edges, and then we union together all of those edges, then that will cover all of the edges in the graph. That's an edge clique cover, and there's no more edges in the union of the C sub alphas than what exists in the graph, because if there is, then that basically means that the graph is saying that there's some sort of independence or conditional independence or some factorization property that doesn't exist in here, right? Because x phi sub alpha can do anything that it wants with the variables C sub alpha, right? It can multiply them together. It could do some crazy nonlinear function. It could do anything. It's assumed that you cannot further decompose the model and break apart these phi functions. Okay? These are the things that cause the variables to directly interact with each other. So the reason why we care about exponential models is because they're going to be, on the one hand, powerful, but they're also sufficient to deal with a lot of the computational aspects of graphical models that we want to talk about with variational inference and the log partition function and all this stuff. And we do have this old result, or this result that it's now old for us, where any graph sort of can be embedded into a graph with more edges, and one possibility would be a triangulated model. But what we don't want to do, we don't want to do that anymore. We want to sort of stay tight. We don't want to solve an exact problem for a more general graph. What we want to do is solve an approximate problem for the specific graph that we've got. This is the approach. So it's like an approximate solution to an exact problem. And interestingly enough, I mean, this should also be clear that any factorization property in a Markov-random field can be respected by an exponential model, depending on what these phi functions are. So, if you take the phi functions, going back to this thing, this vector, and we just multiply exp of each one of them, then those are the factors. So this is sort of I think this is a little bit of a mixed notation from the old notation and the new notation. But what I really want to say here is that if I write p of x, which is equal to the product over alpha of exp of phi of alpha x, and that whole thing times exp of a of theta, which is the log partition function, then this expression here essentially gives us the same factorization properties than what we talked about, except that the factors correspond to the exp of the phis. Okay. So let's just cross this stuff off because we're not using this notation anymore. So this includes log linear models. So log linear models means that basically when you take the log of the probability distribution, you're linear in the parameters theta. But log linear models are very powerful. And strangely enough, and this seems strange, the log partition function is going to essentially give us everything. Once we've got the log partition function expressed in an amenable form, we can do inference. And we can get the marginals. Now, how are we going to do that, and how can we do that? That's what we're going to spend several weeks doing. And if we can get an approximation of the log partition function, we can get an approximation of the marginals. If we can get a bounded approximation of the log partition function, we can get bounded approximation of the marginals. So it's all, in some sense, about the log partition function. And that's not obvious. I want to talk a little bit about absolutely continuous, because the book uses it. We don't need to get so deeply entrenched in the Lebesgue theory and the measure theoretic aspects of the book, although they are attempting to be precise. I have the feeling that basically, and I probably shouldn't say this on video, but that on the one hand, if you were a hardcore mathematical measure theorist, you look at this book and you say, they're just doing it all wrong. It's just trivial. They're not treating measure theory things right. Whereas if you're sort of like a discrete computer scientist who's not used to measure theory, you're thinking, oh no, measures, that's scary. So they're sort of happily in the middle and probably equally disliked by the discrete computer scientist and the real analyst. But I don't know. Take your position on this book, and we're going to probably take more of the position of the discrete computer scientist in this class at least. But you should at least know that basically you can take an integration with respect to some measure. And the measure is nice for a variety of reasons, because it allows us, on the one hand, to deal with both discrete and continuous distributions within the same framework. Like, for example, if it's what's called a counting measure, then that integral, which is really a Lebesgue integral, corresponds to the sum over a set of discrete values. And if it's more of like a Riemannian integral, if it's continuous distribution, you can get this thing which is more like an integral. But it also might be, in some sense, the domain. The domain is sort of also represented in here. Like, it could be the case that we're doing the sum over I in some, say, domain f of x of I, where the domain are the sort of the measurable sets, and everything that's not measurable essentially is 0. So what they're doing in this book is, even though exponential models are sort of never 0, like, because unless you have the phi functions, you might have noticed, mapped to the reals, not to the extended reals. And so if you don't map to the extended reals, that means that you can never map to negative infinity, which means that you can never get the value 0. Nothing can ever have a probability of 0. And so how do you deal with that? Well, you don't deal with it by essentially allowing the phi functions to map to the extended reals. What you do instead is you say, oh, let the measure handle that. So this little guy here is just sort of hiding any zeros, and essentially you can sort of not deal with them and still deal with exponential models. And anything that is 0, you sort of put that into the measure. Okay, but that's not really something that's mentioned too much in the book. The other notion that's important is that that if you've got some base measure nu, so nu is the name of the measure. Where's nu? Then the notion of p, a probability distribution being absolutely continuous with respect to nu. And the basic idea there is the following. It's essentially saying like whenever the measure nu is 0, p also has to be 0. Okay, that's the idea. And so we say that in general, nu is absolutely continuous with respect to some other measure, mu, if it's the case that for each measurable set A, so F is all measurable sets, that if mu gives A a 0 measure, then nu must give A a 0 measure. And you can also write it as nu being dominated by mu. Nu is dominated by mu. Or yet another way of saying it is that if mu goes to 0, so must nu. And here's sort of this picture sort of describing it. So the idea is that nu and mu can do all sorts of stuff, but if it's the case that we ever get to the point where nu comes down, then mu comes down, then nu has to also come down to 0. So mu forces nu to 0. Yep.
Is the v measure, is that going to be the integral?
Nu?
Yeah.
It's not v, it's nu. I know, sorry. Greek letters. Don't.
Is that going to be the integral? What is v defined as?
Nu is just the measure. So it's the measure that you're taking the integral with respect to. So it's a Lebesgue integration. It's not Riemannian integration. So like I said, it's sort of something, when you do Lebesgue integration, there's a formal definition of Lebesgue integration, but when you do it, it's possible to use one framework, integration, to represent both standard sums, like this stuff here, and standard Riemannian integrals, and also domain restrictions, all within the same framework. Okay, so let's skip over this. So when you have an exponential family, you have a set of canonical parameters theta. We have this family of models. So this is maybe a more typical way. You have exp of this dot product, and this is the partition function 1 over z of theta. Z is a function of theta because if you change theta, you're going to change the normalization constant. And the way that we do it here is we just stick it up in the exponent, where a is the log partition function. A of theta is the log partition function. This is the partition function. This is the log partition function. So a of theta is equal to log of z of theta. And we're mostly going to be dealing with the log partition function. We're also going to just assume that the parameters theta are such that the log partition function is finite. Yeah, question?
Yeah, I've seen other forms of the exponential family definition where some of the x's aren't attached to the thetas. So like you might have them floating around. Like so you have x, all the x's are multiplied by parameters. But then there's some x's where they're kind of like the a of theta, it's just like a floating term.
I'm not sure what you mean by a floating term.
Like it's not like all the x's in this form is multiplied to the theta, right?
All the x's are fed through a statistic, which is phi, which is then multiplied by a theta.
But
so you could have other, it could be that phi is an identity.
Oh, okay. So
we're not saying what the statistics are. And we're just saying this is a very general framework. We're going to do some examples in a minute. But one possible phi sub alpha could be just choosing one x and just saying, there you go. And then you've got a theta associated with that one x. Or it might be, as we're going to see, an indicator of x being a value. We're going to see a bunch of examples of how we can represent things, including like Gaussian distributions and Bernoulli distributions, which might seem like they're very, very different, but in fact they're both exponential family models. Yep, question? Oh, no question? Okay. So we're just going to define this domain omega to be the ones for which this integral exists. So there's the integral. It's the log. This is the summation. This is the thing. So we're doing it with respect to measure nu, right? So we're only summing over with respect to measure nu, and we're summing. The book also has this subscript here, which basically indicates the domain of x. But I personally think that you don't need that, so I'm going to cross it off in the slide, because you can actually just stick that into the measure and just say, okay, you're summing over everything, but only over the measurable sets. And so you don't need, it's sort of redundant to say, well, the domain and also the measure. Okay. So that's where the measure theorist would get angry. So then, oh, the other thing, yes, right, so this is really important. So the log partition function is convex. It's a convex function of theta. And that's just basically looking at this expression. It's the log of a sum of ex. That's a convex function. It's just a known convex function. And so therefore, this means that omega, this domain, is a convex domain. So that will be very powerful for us. How can I highlight that more? Okay, convex. I can do that in red. What's a more noticeable color, red or green? Red? Okay, let's do it in red. If anyone asks me this, is that convex? Oops, wrong color. There we go. Okay. And also the notion of a regular family. It's the case when theta is an open interval. This gets into a technicality that I don't think we need to worry too much about at this moment. But you might wonder, like, where might this family come from? Exponential families actually can be seen as coming from the result of a maximum entropy estimation problem, and we're going to define what that means. But basically, here's how you set it up. So let's say you've got a bunch of data, and this is our training data. It's like maybe the evidence, so just to write this, what this means. So we've got m samples of data of just maybe the evidence variables e, and there's a bar over it, which means that these things are observed, and there's a superscript I, which is basically which sample it is. Okay? And these are samples from some distribution. Okay? And so we can construct these various means. For every alpha, we construct the mean of the statistics over the samples. Okay? So we know from the central limit theorem that if it's the case that the size of the samples go to infinity, and we're really drawing from this distribution, that this empirical mean converges to the true mean with respect to the distribution that you're drawing the samples from, and that's equal to mu sub alpha. Okay. Now this, I'm going to say this a few times because this is a little bit tricky. So this is the mu sub alpha is the mean of the statistic at alpha, or it's the mean of the feature, meaning the expected value according to p, the true distribution that we're getting Janing data from. It's the mean of that statistic or that feature. But when we're talking about like other kinds of distributions, we actually might compute the mean of the random variables. And these are really different things. And it's a little bit confusing when we talk about Gaussians, because in Gaussians there's like a mean and a covariance. As we're going to see, both the mean and the correlation matrix are both means. And we will say this. But just be wary that mu sub alpha, really we're just talking about the means of the features in the case of an exponential model, which might not have exactly the same meaning of means as means typically have. And I mean that in a nice way. Nobody gets these jokes. Okay, so what is the machine learning problem in this context, or the estimation problem? Basically, it's defined P star that maximizes the entropy of the distribution. So it's finding the distribution over all universes of distributions, U, subject to the constraint that with respect to the distribution P that we find, and we take the expected value of that feature function, we are equal to our empirical mean. That's the max n problem. So this is a really important problem. Let's just erase that so you can see it. And this is the standard entropy, the standard entropy of a distribution, which could be the continuous distribution or the discrete distribution entropy. In general, the entropy is estimated with respect to the measure nu. Okay, so you integrate over all x with respect to nu of the negative of p log p. Okay, so everybody know what the entropy is. So this is like a mean value of the distribution P with respect to the potential function phi. So it's like a form of moment matching, because you can say, okay, well, if these statistics are like moments, we say we want whatever distribution we get, we want one that matches these moments that we've empirically found, but otherwise the entropy should be maximum. Like anything else that isn't constrained should be of max n, and so therefore we should have maximal uncertainty about that. And that's generally, I mean, that's a very sort of philosophically nice Occam's razor-like thing. It's like, okay, well, I've got these features, and I know that the data says that these features should be this in the mean, but that doesn't constrain me. That still leaves me with an uncountably infinite number of distributions. Okay, so, well, how do I resolve from amongst all of these uncountably infinite distributions? How do I choose the one I want? Well, philosophically, you want the one that makes the least additional assumptions. And the one that makes the least additional assumptions is the one that has maximum entropy. It's the most uncertainty. It's expressing the least. It's saying, well, I don't know anything else, and so therefore I want to sort of make the least. I want to say the least about stuff I don't know, because that sort of is like an insurance policy. It keeps you from saying things that you have no reason to say. It keeps you from saying and making inferences that are not stated in your training data as measured via the potential function's phi. Okay, any questions on maxent? Yep.
So why don't you enforce other moments also, like for example covariance kind of things?
Who's saying that we're not doing that here? Who's saying we're not? We could be. I mean, these phi functions can be very general.
No, between a pair of phis, whatever be the observed covariance between a pair of phis. Right?
A pair of phis.
Yeah.
So what's to keep me from defining a phi which is equal to a pair of phis, of your phis?
It might make the graphical model more connected.
Well, you're always respecting some graphical models, right? So whatever the phis, in some sense, define the graphical model, right? Because anytime there's variables that interact and that cause a lack of factorization in the underlying probability distribution, we are essentially defining a graphical model, right? So you said, like, what's to keep us from relating a pair of phis together? Nothing. I mean, basically, that could just be a new phi. If you say phi sub alpha 1 is equal to phi sub alpha 2 times phi sub alpha 3, that's perfectly fine.
The variance of one particular phi, like the variance with respect to a probability distribution of one particular phi alpha.
So then variance is related to the square of the random variables. So you'd say a phi sub alpha is equal to x sub, the corresponding x squared or something, or x times y. Or you could do cumulants, x times y times z. Or sorry, x sub xi times x sub j times x sub k. This is very, very general. So anytime you want a feature, you just add a new element into I, add a new function phi. So this is, I mean, there's nothing that keeps us from doing any of this stuff. You'll see an example of this a little bit we're going to talk about Gaussians in a minute, and I think this will answer your question. But it's very general. It turns out that, I mean, I'm not going to show this, but and this is shown, maybe you've seen this before in your machine learning classes, that the solution to this problem up here has, strangely enough, a parametric form that looks like this, which is the exponential family. So that is the mathematical form of solution. Here's the log partition function. And the only constraint is that, of course, you have to achieve these moments. So in other words, you don't need to deal with maximum entropy. What you could do is just say, okay, start with equation 11.20, and then make sure that you found the canonical parameters theta that are such that you've achieve these guys. Okay. And that you're going to be shocked, we're not going to get a chance to talk about it today, or maybe surprised to know that that actually corresponds to a maximum likelihood estimation problem. So you'll see that in a minute. But before we do that, let's talk a little bit about this notion of a minimal representation, because I think this is something that I hope, if you haven't read the chapter 3, you should really think about it a little bit, because it's a little bit tricky. But basically, the idea of there's sort of two representations here that we're going to be talking about: minimal representations and over-complete representations, both of which are going to be useful, and both of which, therefore, you need to understand. A minimal representation is one for which it's the case that you can never find a non-zero vector gamma such that this inner product is a constant for all measurable x. Okay, so in other words, obviously, if gamma is all 0, then the inner product is going to be 0. But you're sort of excluding that all 0 case. But a minimal representation is for which there's no gamma for which that's true. So another way of writing this is that it's saying for all non-zero guys, for all non-zero gamma, that means that there exists an x1 and x2 that are not equal to each other, that are both measurable, and that these inner products are not the same value. So another way of sort of seeing this, and again, I think that you will have to just think about this, but here's something that gives you a sort of an intuitive idea. It's basically saying that you have sort of there's this notion of minimal sufficient statistics, and it's basically saying that statistics, and there's not a lower dimensional set of statistics that's also sufficient. So it's a minimal set of sufficient statistics. So there is no such I prime which is also sufficient. And sufficient essentially means that it's sort of sufficient to define the probability distribution. You can add redundant statistics to a set of minimal sufficient statistics, and they can still be sufficient. It doesn't sort of change the distribution. So in other words, we can't reduce the dimensionality of the set of statistics without actually changing the family of distributions that we're talking about. Now, the opposite of a minimal representation is an over-complete representation, where the dimensionality is higher than it needs to be, and that essentially means that there exists a gamma, a non-zero gamma, such that this inner product is identically equal to some constant. And we're running out of time, but let me just briefly do this. So basically, if it's over-complete, and if you take some gamma which is not equal to 0, then this is a constant. And so what you get is that this probability distribution, P of theta plus gamma, which is equal to this thing, but that, because of the properties of the inner product, can be represented as this. And that just is equal to this constant here. But then when we have this, just because it's the normalization constant, it has to be a normalized distribution. It has to equal to this. So basically, C minus the log partition function of theta plus gamma has to be equal to the log partition function, negative log partition function of theta, because of the normalization constraint. And so therefore we're back to this. So this, it's sort of like there's this affine dimension, gamma, where nothing changes, where the distribution is exactly the same. So you can move in this affine dimension. You can think about it in this way, like there might be a whole bunch of affine dimensions where if you move up and down on this affine dimension, in this, then you're not actually changing the probability distribution. The distribution is really only changing along this direction. So that would be an over-complete representation. Okay, we are out of time. Please read Chapter 3. It will make Monday's lecture fun and exciting and exhilarating. I will see you on Monday.